Hello, EP chemistry students. We are going to do kind of a quick overview on ionic bonding. So we'll go through ionic bonding and then also get into lattice energy. So ionic bonding is all about the transfer of electrons from a metal atom to non-metal atoms that then form positive and negative ions that are going to attract each other and form a solid compound. In an ionic bonding, the total number of electrons lost by the metal atoms is always going to be equal to the total number of electrons gained by the nonmetal. That just goes back to like conservation of charge, which follows right along with what we've talked about previously with conservation of mass, conservation of energy. So this all involves, again, an electron transfer. We have two atoms. An electron is moved from the metal to the nonmetal. They form ions, and then this attraction occurs between those ions to form the bond. Now, energy is actually absorbed during this electron transfer. And if an absorption of energy, which is endothermic, is actually unfavorable, why do these ionic compounds form? And that has to do with that attraction between the ions. When they come together, is actually going to release a large amount of energy. So there is a much larger amount of energy that's released when our gaseous ions are going to actually come together, attract each other, and form the solid. So this is related to lattice energy. You've seen in the POCL that you might have done in class, where we actually have a negative lattice energy, which is showing a release of energy when those ions attract each other. This all goes under the Born-Haber cycle, which is a series of steps from elements to an ionic compound with known enthalpies. So if you look at the starting point right here, okay, you can see that there's an absorption of energy that occurs as an electron is transferred. So you can see here we can see enthalpy of sublation. Here's our ionization energy when that cesium is going to lose an electron and forms a +1 ion. And then we have a dissociation energy for the F2 breaking apart. And then we can see that the fluorine atom here is going to gain an electron. So we can look at our electron affinity when that fluorine atom becomes a fluorine ion. So you should see some things familiar here talking about ionization energy, electron affinity. All of these play into the formation of our ions. And then the last step that we're most interested in is this one here. Okay, that now that we've formed our positive and negative ion, that attraction between them is going to release a large amount of energy to then form our solid ionic compound. This is what makes this process favorable and why we see an overall change in a negative change, meaning it's exothermic, which tend to be favorable processes. So one little thing I want you to add in over here, just to make sure you understand the value in this, is that again, the negative lattice energy signifies a release of energy. Okay, the larger the magnitude, and that means the amount, not the sign out in front, but the amount, the greater amount released. Okay, which for us means that indicates a stronger attraction between the ions, and thus a stronger bond between the ions. And we're going to get into that specifically of what factors affect the strength of that attraction and bond and why we might get a smaller or greater magnitude of lattice energy. So we will come back to that. So one little thing that I want to talk about, 3 ways to depict ionic bonding. And it has to do with we show this transfer of electrons. So we're going to be using lithium fluoride, or the formation of the lithium fluoride ion or compound. So if you think about, we have a lithium atom and a fluoride or fluorine atom. If we look at their electron configurations, lithium is 1s2, 2s1, plus if we have a fluorine atom, we would have 1s2, 2s2, 2p5. Okay, that one electron here in 2s is going to get transferred to the fluorine atom. So when we end up with our lithium ion, we're going to get a +1 charge, and its new configuration is simply 1s2. And then our fluorine atom is going to become a fluoride ion, and it's going to have a -1 charge, and its new configuration is going to be 1s2, 2s2, 2p6. So that's one way to show this transfer of electrons that would then form our lithium fluoride compound. Another way is simply just using orbital diagrams. I'm going to put them above and below each other just because of space. So we know that we have our 1s and our 2s. So we have 2 and 1s, 1 and 2s. And then for our fluoride ion, we have 1s, 2s, and 3 orbitals in 2p. So we have a full 1s and 2s, and then 2p just has 5 electrons in it. So for this little piece here, think about the fact that, again, it's going to be this electron that's going to be transferred to our fluorine ion, and then the change afterwards would be our lithium ion, which now is just a full 1s, and our fluoride ion, which now has full orbitals. So a full 1s, full 2s, and then a full 2p. So that's another way to depict ionic bonding. So just be aware of both of those, how we can use either our electron configurations or our orbital diagrams. Probably the most common way is using our Lewis electron symbols in order to illustrate the transfer of electrons and the compound form between. So if you think about valence electrons, lithium has 1 valence electron, okay, and fluorine has 7. And you can do that by looking at their electron configurations, the groups that they're in. Now, we have said already that ionic bonding is all about the transfer of electrons. That metal is going to transfer its electron to fluorine. Lithium now has a +1 charge and has lost its valence electron. Fluorine now has 8 electrons around it. We're then going to put brackets around it to signify that those electrons are only a part of fluorine, and we put the charge of it on the outside of the brackets. When those two ions form, they're then going to attract each other. So we'll actually just write them right next to each other. We have our lithium ion, ionically bonded now with our fluoride ion. Okay, these would then exist in a crystal lattice. As a solid. Okay, so definitely feel comfortable when you're practicing drawing these. Start with your Lewis dot diagrams, show that transfer of electrons, and make sure also that your charges end up with a neutral compound. So this is one where it was just 1 to 1. All right, the other part that we want to talk about is lattice energy, and just summarize what you saw in the POGL. So lattice energy, we already mentioned, is a change in energy when 1 mole of ions in their gaseous state form an ionic solid. Again, it's going to be the attraction between them. You can also consider it as being equivalent to the energy required to separate that 1 mole of ions from the ionic solid to their gaseous ion. So you can think about if you were to break the bond, how much energy would have to be absorbed. But usually the true definition of lattice energy is really when those are going to form the ionic solid and attract each other. So lattice energy is a measure of strength of the ionic bond. We know that this results from the electrostatic interactions among the ions. So the magnitude of the lattice energy is going to depend on a couple of things. We are going to focus on ionic size and ionic charge, but it also has to do with the arrangement of ions in a solid as well. So we've talked about Coulomb's law already, about how the amount of charge, which is our Q values in the formula, and our distance between the charges, which is R here in our formula, are both going to impact the magnitude of the force of attraction. So lattice energy is affected, just like we learned about with Coulombic attraction before. It's all going to be about distance and charge. So for us, lattice energy is affected by the radii of the ions. So we find that as the ionic radius increases, okay, the greater distance between, okay, between our charges, which are our ions. Okay, this results in a weaker attraction. Between our ions. Which will cause a decrease in lattice energy. So you can kind of see here if we look at going from, in this case, lithium fluoride down through our group 1 ions. Here the fluoride ion is staying constant, and then we're moving from our +1 lithium through our group 1 ions to rubidium. As the radius increases, you can see that the lattice energy is going to decrease. Okay, so as again, ionic radius increases, our lattice energy is going to decrease. It all goes back to that greater distance between the charges. All right, the other big factor that we have to be concerned with is the charges of the ions. And really, this is the first thing I look at when I'm looking at ionic bonds in terms of determining the strength. So as the ionic charge or charges, and really we're talking about the magnitude of it. So as it increases, so whether it goes from like +1 to +2 to +3, or again, ignoring the sign, if I go from -1 to -2 to -3, so if I'm increasing the magnitude of the charge, the stronger the attraction. Between the ions. Which will cause a greater attraction when those ions come together, which will increase the lattice energy. Okay, so as ionic charge increases, we get a stronger attraction between the ions that will then increase the lattice energy. So when we look at, so you can kind of see that if you were to look at increasing the charge down here, we have a +1 Na and a -1 F. If I then look at relatively similar radii of magnesium oxide, I'm looking at a +2 and a -2. So not a huge difference in the change in radii. The biggest difference between these lattice energies is simply that change in charge, where the +2 -2 charge creates a much greater lattice energy. So when you're comparing various groups, the greatest lattice energy, you're looking for the ionic compound with the smallest radii with the greatest charge. So the smallest radii with the greatest charge is going to give you that greatest lattice energy. And just remember, greatest lattice energy is the strongest attraction between. Okay, well, that's basically it. So we gave kind of a brief overview of ionic bonding and lattice energy. And I do want to get into just quickly reviewing properties of ionic compounds. We'll come back to this at the end of the unit when we go through all different types of solids. But just so you have an idea and can answer some basic questions about it. One big thing is with properties of ionic compounds. Ionic compounds tend to be hard materials. They're rigid, so they don't easily bend. And they're brittle, they crack without deforming. This is much different than when we talked about metallic solids, which are malleable and ductile. And that's because of the ions that are involved with ionic compounds. There's strong attractive forces between them. When you're moving them out of position, that requires overcoming those forces. So there's going to be some energy involved. And if enough force is applied, ions of like charge are brought next to each other, and then there's a repulsion that occurs between them. So let me just see if I can magnify this over on the side just a little bit. So you'll see here we have attractions that occur between these ions here where they're attracting each other. All of a sudden, when we use enough force, we'll see positive ions next to each other, negative ions next to each other, and those are going to repel from each other. And then we actually get a crack in the crystal. So that's what it's talking about, why it's different than what we mentioned before with metallic bonds. The ionic bonds and the characteristics of ionic bonds give it very different properties. The other thing that makes it different than when we've talked about so far metallic bonding is that ionic solids can only conduct when melted or dissolved, but do not conduct in the solid state. So just remember, when we talk about conducting, there has to be a charge that can move. So the thing with ionic compounds is when we have solid ionic compounds, there is a charge there. We have positive and negative charges in an ionic compound. However, those charge ions are locked in place. So charge ions are locked in a crystal lattice equals solids unable to conduct. Okay, however, if we melt the ionic compound or we dissolve it in water, in both of those cases, our ions now have mobility. Okay, which means they are able to conduct. Okay, so that's one big difference from how we'll distinguish it from other types of compounds. It's this idea that, yes, it can conduct when it's melted or dissolved, but will not be able to conduct in the solid state. And that just has to do with solids having their ions locked in a crystal lattice, unable to move. Last little part here. Ionic compounds have high melting points and even higher boiling points. It takes a lot of energy to free those ions from their crystal lattice positions and to separate them. So it's going to take a lot of energy, especially when we talk about trying to actually vaporize and completely overcome the attractions to form gaseous ionic compounds. Okay, so for practice, you're going to be going through and writing out, do at least one with the electron configurations, and the Lewis dot symbols is really the one that I want you to write for all of them to show kind of the transfer of electrons and how you get the final piece there. Just be very careful. I would almost write out the formula personally. So like if you're doing Ba and Cl, we know that Ba from our formula writing forms a +2 and chlorines will form a -1 ion. So keep in mind your final product should represent barium chloride, BaCl2. So we'll just do this one together. If you have barium, which has 2, okay, and then I'm just going to draw this in a different color so you can see the difference here. And then I'm going to have my 2 chlorines. They each have 7 valence electrons. So you should be able to see that the barium is going to transfer 1 electron to each chlorines here. So we'll have our barium ion, which will have a 2+ charge. And then we will have our chloride ions. And I'm just going to draw all the dots in blue just to save time. With their 8 valence electrons. Okay, so barium has no dots, has to have its +2 charge there. Chlorines now have to have 8 valence electrons with brackets, and they have to have that -1 charge there. So that's what you should be working on through that part here, and then you'll see a little bit more with the practice. All right, you are all set.